By the way,
Ah,
was my audio please, if anyone wants to interrupt me, particularly because it's a small group, I don't mind. You know, this is for your benefit. Um, so if you want to stop me or if you want me to go faster or slower, that's fine. Okay, so the topic is going to be, it's number theory again, but it's unique factorization. And what that means is that we've got the natural numbers, n, which I mentioned last week. And I also mentioned the integers, or the whole numbers. And it's about the way you can factorize integers into primes. So let's just recall what you probably already know. P, an integer, is said to be prime if its only divisors are, well, you can always divide by 1 or -1 and the number itself. So the list of primes, we start with 2, 3, 5, 7, 11, 13, and so on. These are all primes. And 4, for instance, is not prime because 4, you have an extra factor, which is 2. Okay, so what is unique factorization? Well, you probably already know this. And I'll give a simple version. This says the following. So the simple version is just, it applies to natural numbers, but you can extend this to any integer. So if n is a natural number, so if n is greater than 1, then n can be written as a product of prime numbers. This is for some prime numbers P1 down to pk, for some k greater than or equal to 1. And the uniqueness is to say that these, and this factorization, is unique in the sense that you can move the primes around, so up to reordering the terms. So simple example, 6 is 3 times 2. Of course, we can also write that as 2 times 3, but these are essentially the same. Okay, so we don't care the order in which we write the primes. Now, I want to give you a proof of a really, really old theorem, and you might have seen this before as well. So it's due to the ancient Greek mathematician Euclid. There are infinitely many primes. And so you can let me know if you've actually seen this proof before. So the proof is what is known as a proof by contradiction. And what that means is that you assume that the statement is false, and you try and get a contradiction from assuming the statement is false. So in this case, the opposite statement is that there are only finitely many primes. So say P1, P2, and Pn are all the primes. And we're going to prove that this leads to a contradiction. So what we do is we form the integer n, and n is defined to be the product p1 times p2 times pn, and then you simply add 1. Now, it's clear that n is greater than 1, so n can be factored as a product of primes. According to the unique factorization theorem. Have you seen this style of argument before? Anyone?
Yeah, I did.
Okay.
I also saw the same proof.
Okay, so I'm going to give it an application which is basically based on this argument, which is the reason why I'm giving it to you. And if you haven't seen this before, anyway, it's worth repeating. So we write n. I'm going to use the primes in n. I'm going to label them as q1. So q's rather than b's, just to distinguish them from the previous ones. So say qk, where the qi are primes, and k is greater than or equal to 1. So now we have an equation that says p1 times pk, pn plus 1 is q1 times q2 qk. So, but p1 up to pn are all the primes. So we consider q1. This is prime. Then by hypothesis, q1 is a prime, is in the list p1 down to pn of all primes. We can arrange the notation so we can say, so without loss of generality. So I'll just say, so by choosing notation, we can assume that q1 equals p1. We can just choose our notation like that. So now we have p1 times p2 times pn plus 1 equals p1 times q2 qk. And then we can rearrange that as p1 into p2 times pn minus q2 times qk. We bring the 1 across the equals, we get minus 1. So p1 divides minus 1, and that's impossible as p1, because it's a prime, is greater than or equal to 2. And the only divisors of minus 1 are plus or minus 1. Okay, so that's a proof of Euclid's theorem. So there are infinitely many primes. You can always find a prime bigger than any prime that you might know. So given any prime, P, there is always prime Q bigger than P. And just as a matter of interest, I'm just throwing out this fact. There's something called Bertrand's postulate. says that we can find prime Q with Q between P and 2P primes, or for any prime P. Okay, so that's quite difficult to prove. So I'm just throwing that out there for your interest. I'm sure you can find articles about that online. Okay, so I want to move on to an application. So this is the Irish Maths Olympiad. So that's what I'll be using for the national competition. From 1990. So we first started participating in the international competitions in, I think, 1988 or 1987. Yeah, so I think 1988. So this was the third competition. And so it goes as follows. So it's paper 1, question 2. And it asks the following. So it says, define primes AN as follows. So first of all, we define A1 to be 2, and for n greater than or equal to 2, AN is the largest. Do I have a comment there? Okay, I'll continue. The largest prime divisor of A1 times A2 times AN minus 1 plus 1. So I think you can see the genesis of this problem is actually Euclid's proof that there are infinitely many primes. Okay, so anyway, the question is as follows. So that's the hypothesis. And the question is to show that AN is not equal to 5 for all n. Okay, so, you know, a typical thing that you do when you're faced with a problem like this is you do a little bit of numerical experimentation. You say, well, what does this look like? So you can actually write down the first, this sequence, at least the first few terms. So let's just do that. So we know that A1 is 2. What about A2? Well, A2 is a prime divisor. So A2 divides A1 plus 1. So A2 is 3, because that's prime. What about A3? So A3 divides A1 times A2 plus 1, which is prime. So we get A3 equals 5, equals 7. And you'll notice that we've got 2, 3, but we've skipped 5. We've gone on to 7. If we keep going, A4, we have to consider 2 by 3 by 7 plus 1, which is 43. And you can check that 43 is prime. So A4 equals 43. And for A5, we've got 2 by 3 by 7 by 43 plus 1. Now, I can't check this offhand, But if you work out that number, it turns out that 139 is the largest prime divisor. So the largest prime divisor is in fact 139. Okay, so what we can conclude from the above, so in particular, notice if an is equal to 5 for some n, we can immediately say that n is well, I got A3 is 7, A4 is 43, so A5 here is 139. So n has to be strictly bigger than 5. Okay, so everyone following this so far?
Yes.
Okay. So we haven't actually got to the substantive part of this. And I guess I will say that this is not a particularly hard problem. But does anyone have any suggestion now for how to continue? Okay, so I'll just continue. Okay, so we're going to do a proof by contradiction. So now we assume, for the sake of contradiction, this is a very useful shorthand. This means for the sake of contradiction. I'd be interested if there's an Arabic version of FSOC, if anyone knows, that in fact an is equal to 5, where now we know that n is at least 6. So we're going to assume this, and then we're going to show that that leads to a contradiction. Okay, so what does that mean? So the only possible prime divisors of A1, A2, down to AN minus 1 plus 1 are, well, they have to be less than or equal to 5, because we're assuming, because AN is 5, that means that 5 is the largest prime divisor of this number here. So what are the possible prime divisors? There's 2, 3, or 5. In other words, when we factorize, when we write this in terms of its prime factors, we can write it as 2 to the alpha times 3 to the beta times 5 to the gamma for some alpha and beta greater than or equal to 0, and gamma is greater than 0, because 5 is a prime divisor. I hope those Greek letters are familiar to you. Okay, so, but A1 equals 2 does not divide the left-hand side. And A2 equals 3, likewise. Because on the left-hand side, you've got 2 times some integer plus 1, and that's going to be an odd integer, so 2 is not going to divide it. And a similar argument tells you that 3 does not divide it, because you're adding 1 onto an integer that's divisible by 3. So 2 does not divide 2m plus 1 for any m. And 3 does not divide 3m plus 1 for any m. Okay, so the conclusion we draw from this is that alpha equals beta equals 0. And so our product is actually just a power of 5. So we'll say 5 to the gamma. Okay, so this looks kind of unlikely, but how are we going to kill this off? How are we going to proceed from here? Does anyone have any idea?
Can you repeat the question?
Do you have any good suggestion for how to proceed, how to continue from this equation? So we're trying to get something, a contradiction. We're trying to show that this is impossible.
So we want to prove that 5 is not the largest prime divisor.
Yeah, but we actually have more because now
We can consider 5 to the power gamma plus 1 is not divided by 5 to the power gamma. It's not divided by 5.
So you're saying that 5 to the gamma plus 1 is not divisible by, what was it again?
By 5.
Yeah. But can we relate this to this equation here?
Oh, no.
But you have done something significant here because it's not plus 1 you need to look at it, it's minus 1. What can we say about that number?
A.
Is that right? Yeah. And what about this number? Is there something significant about this? Let's just have a look at some values of gamma. And then 5 to the gamma minus 1. So gamma is at least 1. So if we take gamma equals 1, we get 4. Gamma equals 2, we get 25 minus 1, which is 24, which is 8 by 3. When gamma is 3, we get 124, which is what? It's 4.
Oh, okay.
4 times 31, is that right? So notice that in all of these cases, I can rewrite this as 4 times 6. See the way 4 divides all of these? So I claim 4 divides 5 to the gamma minus 1 if gamma is greater than or equal to 1. Now, we haven't done modular arithmetic, but have you heard the term modular arithmetic?
I guess I heard about them, but we specifically, like for me, I took in school sequences, not arithmetic, or we didn't get deep in arithmetic.
Okay, so this is one of the topics that's very useful in the Olympiad. So I can give you, because it's come up, I will give you there's a few ways of tackling this 5 to the gamma minus 1. So one of them is using modular arithmetic. So here's the idea. So I'll give you let's see it's a very, very brief idea of what's going on. Okay, so apologies for kind of simplifying things, but here's the idea. So just ignore the problem above for the minute. So the idea is the following. We take some integer n, which has to be greater than 1. And then if you remember from last week, we had the division algorithm. So n here, we're going to call the modulus. So we're going to fix n. So the division algorithm says the following. Say we've got an integer a, and let's just assume it's greater than 1. So I'm just doing this for the natural numbers, but you can do this for any integer. Then we can write a as a multiple of n and a remainder. And the remainder, so q and r are integers. And the key point is the remainder is somewhere, it's strictly less than n. So we call for the residue, it's like what's left over, the residue of a mod stands for modulo n. So this is a phrase that you use. So let's have a look at what happens when, I'll do it because it arises in this problem. Let's have a look at what happens when n equals 4. So I'm going to write down my values of a, and then I'll write below it the corresponding value of the residue. So when a is 0, okay, I said a is positive, but let's say a is just greater than or equal to 0. The residue or the remainder is going to be 0. When a is 1, you get 1. When a is 2, you get 2. When a is 3, you get 3. Now, something interesting happens with 4, because now 4 is 1 times 4, and the remainder is 0. So the residue is 0. For 5, you get 1, because you can write 5 as 1 times 4 plus 1. 6, you're going to get 2. 7, you get 3. 8, you get 0 again. So can you see the pattern?
Yeah.
Okay, so I mean, if you've seen this before, it's very simple. If you haven't seen it before, it's also very simple. The point is, it's like a circle. You're going around a circle, and the circle has 4 marks on it. And you can imagine getting your entire number line. So this is the integers. 0, 1, 2, 3, 4, 5, minus 1, minus 2. And you can wrap it around the circle. I'm just trying to make a neater circle here. Oops, anyway, it's not a circle, it's an ellipse. Okay, doesn't really matter. Let's see, something like that. Okay, and it repeats itself. So it's a repeating or a periodic function. Okay, and that's the residue function. And here's the really amazing thing. So what I'm going to do is I'm going to write R as a bar. So this is for fixed n. So a bar, so we can write a as q n plus a bar, where a bar is the residue. course, the meaning of the bar depends on n. If you change n, a bar means something different, but because we're fixing n, we get that. Here's the key fact. There's two key facts. If you've got two integers a and b, then you can compare the residue of a plus b and the residue of a and the residue of b. And it turns out that you basically get this, where here we're taking, you add the residues and then take the residue of the result. So I'll just give you an example for n equals 4. So you can make up a table, and I'm not going to put bars on things. I'll just do the possible residues mod 4. There's 0, 1, 2, and 3. And then 0, 1, 2, and 3. Now, if I add, what does residue 0 mean? Well, that means that 4 divides the number. And if you add two numbers which are divisible by 4, the result is still divisible by 4. But if you add something divisible by 4 to something where the remainder is 1, when you add them, the remainder is going to be 1. And likewise, here you get 2 and 3. And then you can add up the residues. 1 plus 1 is 2. 1 plus 2 is 3. Now, 1 plus 3 is 4, but the residue of 4 is 0. And 2 plus 2 is 4, and that residue is 0. 2 plus 3 is 5, but the residue of 5 is 1. And then 3 plus 3 is 6. But 6 leaves a residue of 2 when you divide by 4. So you've got 6 is 1 times 4 plus 2. So you get a 2 here. Okay, so some of you have probably seen these kind of tables before, but is that making sense?
Yeah, that makes sense.
Okay, and now miraculously, you've got the same thing going on for multiplication. So the residue of a times b is the residue of a times the residue of b. So I can do the same table for multiplication. Now here, it's if you hit something divisible by 4 with anything else, you get 0. So it's a bit like, well, that is multiplication. And then 1 doesn't change the residue, multiplication by 1. Multiplication by 2, well, 2 by 2 is 4, so you get a 0. And 2 threes is 6, which gives you a residue of 2. And then likewise here. And then 3 threes is 9. And 9 is 2 times 4 plus 1. So you get a remainder of 1 there. Okay, so this is these are called the multiplication tables, the addition and multiplication tables modulo 4 in this case. Okay, so what has this got to do with our original problem? So now consider 5 to the gamma minus 1. Can anyone see where this is going?
What did you want?
So this is what was
For
occurred in the
gamma.
problem.
For gamma is greater or greater than or equal to 1,
That's right.
it's always 0. But if the remainder is always 0.
Yeah, exactly. So what we have is 5 has a remainder. One, mod 4, which I could write as 5 bar equals 1. So 5 by 5 bar is 1 bar times 1 bar, which is 1 bar. And 5 cubed bar is 5 bar times 1 bar, which is 1 bar times 1 bar equals 1 bar, etc. In other words, 5 to the gamma bar equals 1 mod 4. Okay, so i.e., we can write 5 to the gamma is a multiple of 4 and a remainder of 1, where q is some number. And so when we subtract 1 from both sides, we get 4q is divisible by 4. And the exclamation mark there is not factorial, it just means that's interesting. Okay, so remember what we had is A1 times A2 times AN minus 1, was it? Is 5 to the gamma minus 1 is divisible by 4. But the left hand side, because we know A1 is 2, the left hand side has the form 2 times A2 times AN minus 1. And these are distinct primes. These are distinct odd primes, hence are odd. So we've got 2 times an odd number is divisible by 4, and that's a contradiction. Okay. So that completes that question. Okay, so I mean, I will put these, I will give these notes to Samit, so you can look at this yourselves if you want. So I've packed quite a bit of different material into that. Just I'll make the following note as well, that you don't need to know this modular stuff to prove this, because you could also note the following. You may have seen this, the sum of a geometric series.
2 times odd is not divisible by 4, not divisible by 4.
Well, it's according to the above, 2 times an odd is divisible by 4, and that's obviously false.
Yeah.
So I'm stating something that's false. So I've arrived at that conclusion, and because it's false, that means that my assumption must have been wrong.
Oh, okay.
So that's the structure of the proof. You assume something, you use that assumption to prove something that's patently false, and then that proves that your original assumption must be incorrect. And the original assumption was that AN was 5. So this shows that AN is in fact not equal to 5. Okay, so that's the idea. It's a bit confusing, but this is a so-called proof by contradiction. Does that make sense?
Yes.
Okay, and that's a common style of argument, particularly in the Olympiad. So you've probably seen this. This comes up when you're looking at compound interest. So you've got some real number r, and you look at 1 plus r squared up to r to the n minus 1. You know what this looks like? This is
Um,
r to the n minus 1 over r minus 1.
is there another rule like by r equal a over r minus 1 or something like that? I'm not sure if that's the same one.
There's the sum of the an arithmetic series.
Oh, okay.
Let's see if I'll write it down and see if it looks familiar. So an arithmetic geometric series is where every term is got from the previous term by multiplying by some fixed number. In this case, you're multiplying each term by r to get the next term, and then you're adding them up. So you go 1 times r is r times r is r squared times r is r cubed, and so on. So that gives you the terms. For an arithmetic series, the terms differ by something fixed. So you might start with the starting term a, and then you add a difference for the next term, and then you add the difference again, and so on.
Okay,
So
I just remember it. Thank you.
okay, and then the sum here, what does the sum look like? So let's say a plus d. Now, you're putting me on the spot. Let's see. So if we've got n terms, we'll get a plus n minus 1d. And you can basically, how many a's do you have? You've got n a's, so you've got an na, and then you've got d into 1 plus 2 all the way down to n minus 1. Do you know what the sum here is? This is a beautiful sum. This is a triangular number. So it's easier if it was expressed in terms of n, but anyway, it's n minus 1 by n over 2, which is also n choose 2. You might have seen that.
Yeah, thank you.
Is that what you were thinking of?
Yeah, that is
Okay.
exactly.
Yeah. And you know why it's called a triangular number as well? Because there you've got 1, 2, 3, 4, 5, and so on. So you're adding up the number of squares in some triangle. And basically the way you look at it is you think of it as there's a rectangle, and you basically have half the area of the rectangle. Anyway, you've probably seen that kind of little trick. Okay. So anyway, the point then is that 5 to the gamma minus 1, you can rewrite it as 5 minus 1. And here, so you're taking, let's see, what are you doing here? Oh, so if you take, so what do I want to say? Yeah, you take r to be 4. Or no, you take r equals 5. And what you get is 1 plus 5 plus 5 to the gamma minus 1 is equal to 5 to the gamma minus 1 divided by 5 minus 1. Now 5 minus 1 is 4. So you actually get 5 to the gamma minus 1 is 4 into 1 plus 5. That's 5 to the gamma minus 1. So the whole point of this is divisible by 4, which we had proved anyway using modular arithmetic. But this is just a kind of a more concrete way of saying it. Okay, so I'll do, this is quite an easy problem. if unless you have any more questions about that. There's a whole bunch of things I could branch off into from any one of these problems. So it's a long established tradition in the Maths Olympiad, the international and the national competitions. People setting the questions, they always like to have a question involving the year. So 2024. Does anyone know the prime factorization of 2024? Oh, is it 2 to the 11? No,
no.
that's no, I was thinking of, go on, sorry. So it's 2 by 1012, which is 4 by 506, which is 8 by 258, is it?
I guess 250.
No,
200,
58.
no,
Oh,
No.
okay.
no, not 58.
48.
No,
Why not?
yeah, 253, sorry.
Oh, okay, yeah.
Yeah. And now 253, is it divisible by anything? I'm going to cheat here and look up Google. I have a feeling it might be divisible by 17. You're probably better at doing this than me. But while you figure it out, I'm going to check on Google. 253. Yeah. Is it 11 by
Yeah.
23? Is that right? So that's 230 plus 23 is 253. Okay, so the prime factorization is 2 cubed times 11 times 23. So anyway, just bear that in mind. That is likely to come up in some problem in the Olympiad. Okay, so here's my problem, and this is quite an okay problem. So the Irish Maths Olympiad, so this is the national training contest. It's the 10th competition, so it was 1997. And just to stress that these national competitions are easier than the international one. So we have kind of 3 levels. We have a local competition, which is at one level, the national competition is harder, and then the international competition is much harder. So this is not at the standard of the international competition. Okay, so the question, this was paper 1. Question 1. And by the way, if you want, I'm just mentioning this because it's available on the internet, but all of these competitions, they're all available from, there's a compendium of the competitions. So I think there's a lecturer called Mark Dukes at University College Dublin. And you can just download a PDF if you want practice questions. But there are so many resources online with competition questions, but I just mentioned that in passing. Okay, and so paper 1, question 1, the question is the following. Find all pairs, x and y. They have to be pairs of integers such that and you can see here we've got the number, the year is 1997, and that's kind of incorporated into the question. That we have 1996, 1998 equals xy. Okay? So this is a so-called Diophantine equation. So that's the problem. This is a Diophantine equation. So you've got an equation in two variables, but you're only interested in the integer solutions. And Diophantine was an ancient Greek mathematician, and the ancient Greeks were interested in these type of problems. They're actually really difficult, usually. This problem is not difficult, but in general, if you're only looking for integer solutions, that's really, really difficult. Okay, so anyone got any ideas how you would do this?
Um,
Okay, I'll maybe give you a hint to think about it. The significance of 1996 and 1998 is it's 1996 is 1997 minus 1, and 1998 is 1997 plus 1.
oh yeah.
So what I'm going to do is, to make things simple, I'm going to write n is 1997. So what we get is 1 plus n minus 1 x plus n plus 1 y equals xy. Now, can anyone see a simplification?
Maybe the square difference between n minus 1 and n plus 1.
Certainly true. Not sure how to use that here.
I was thinking about to take x and y as a common factor, then to apply the difference square. But I'm not sure if it's like right.
Yeah. So it's not quite clear. I mean, the equation, there is a kind of a factorization hidden there. So maybe if I write it down and see if you can do anything with it. So the idea is that if you leave the ends on the right hand side, so I'm going to rewrite the right hand side as 1 plus, let's see, I'll write it like this. So I'll keep the part that's involving n. So we've got n into x plus y. I'll just put that in brackets. That depends on n. What doesn't depend on n is you've got 1 minus x plus y. That's equal to xy. Agreed?
Yes, agreed.
Okay, so now I'm going to rearrange things with my magical iPad. And then I bring that across and it becomes a minus. Okay? I hope that's okay. And now, can anyone see the factorization of this? So let's just rewrite that. You've got minus 1 plus x minus y. I think that's correct. So I'd like to factorize that term. And I could even rewrite it like this.
Maybe we could take like y as a common factor, then y equal for something and the
So we
inside.
have x
Yeah.
minus 1 times y, and then the remainder is x minus 1. Yeah,
Yes.
and now we can rewrite that. We've got x minus 1 now as a common factor, so we can actually write it as y plus 1. Well done. Okay, so that's
I can't understand this.
so that was Liam, was it, a minute ago? I mean, these are kind of little tricks. So let's have a look at this again. How did I get that factorization? So you think of it, what I'm pulling out the y first. So we've got x times y and minus 1 times y. Okay, and then the remaining part is x minus 1. So you agree with that?
Oh, yeah.
And now you've got an x minus 1 term that you can pull out. So you've got x minus 1 into y, and then you've got a 1 times x minus 1. So that's how we got that.
So the question just like if we just right now type that x equal 1 and y equal minus 1, is that appropriate of what the question needs, or we have to do another step?
Yeah, I'm not sure now. I think this let's see, it's not clear at all now if we can proceed using this. The other fact here is n is 1997, and it turns out, I can't see this immediately, but n is prime. So let's have a look at this again. In fact, I think I may have led you astray here, but anyway, let's have a look at 1 plus n minus 1 x plus n plus 1 y minus xy equals 0. So let's see, can we factorize this? And so I'm claiming that if we look at x minus n plus 1 by y minus n minus 1, what do we get if we multiply that out? So that's what we're trying to solve. I've just rewritten the original equation slightly there. But if I look at this expression and multiply it out, I get, okay, I've got the wrong sign, but I've got an xy minus n plus 1y minus n minus 1x. And then what do we have? Oh, we have our n squared minus 1, don't we? What do we have? We've got plus n plus 1 by n minus 1. And that is n squared minus 1. So if we make sense of this, what do we know about this? Well, if you compare it with this, we basically have this bit and this bit add up to 0. So this whole thing is n squared. Does that make sense?
Yes.
Okay. So in fact, your comment at the beginning about n plus 1 by n minus 1 is equal to n squared minus 1 was relevant. So finally, what we have is that x minus n plus 1 by y minus n minus 1 is equal to n squared. And n is prime. Now n is 1997. And now we're in a good shape because the factors of the right-hand side are just 1, n, and n squared. So it turns out that we have we've got two factors here, x minus n minus 1, and this is y minus n plus 1. So by unique factorization, here are the possibilities for, I'm going to call this A, and this is B. So A and B are factors of n squared, and n squared is prime. So A could be 1, in which case B is n squared. Or A could be n, in which case B is n. Or A could be n squared, and then B is 1. And then we can also have plus or minus. So I'll say plus or minus A, plus or minus B. And if you look at the possibilities, you will get 6 solutions. I think in this case, there's A and B have to be positive. So you get 4, 5, let's see, you get 4 solutions. And then, oh yeah, you can, no. Let's see, you must have, so in this case, A is positive. And in this case, B is positive. And here you've got 2 solutions. So I'm not seeing this right, but anyway, basically you have solutions like you've got things like x minus n minus 1 is plus 1, in which case y minus n minus 1, or is it plus 1, is n squared. And that gives you a solution for x and y, or x minus n minus 1 is minus 1, in which case y minus n plus 1 is minus n squared, etc. So I'm not going to write them down, but you get a whole bunch of solutions, and I think it's 6 solutions in all, according to what the solution I looked at. Okay, so I think I've kind of gone over, so maybe I should stop here if that's okay, or unless anyone wants to make any comment or ask me any question.
I love the way that today's session was like to solve some question.
Good. So it probably makes it more interesting, does it?
Yeah.
So I have to say on this one, you can see that I went down on a sidetrack here with the factorization. It's, in these kind of problems, it's not always clear what to do, and you might have to try several things. That's all I can say. So this key fact here, it's not at all clear. I'll just say question mark. How do you do that? I don't know. Why do you look at that? You just have to experiment a lot of the time.
Yes.
And you have to be prepared to, try things out. So if you ever look at someone's solutions, they tend to be a big mess because that's the way people think. They think, I'll try that, and then you gotta, that's what I'm gonna try. So yeah, it's not a kind of a straight line. You go from question to solution. It's obvious. A lot of the time it won't be obvious. And what makes the international competition harder than the national ones is that they tend to get you to do, you have to have maybe 2 or 3 kind of moments of, that's what you do. So 1 isn't enough. You kind of have to make 2 or 3 lucky guesses. So the easier problems, you just have to see one thing, and then you can proceed to the solution. But for the harder problems, you have to have one insight, and then even when you've got that one insight, you have to have a subsequent insight. So, yeah.
Thank you for the advice.
Okay, it may not help at all. Okay, so we'll leave it there. I'll talk to Samid about whether it will be worthwhile next week or between now and June in continuing these kind of sessions. But anyway, for the minute, best of luck on Monday. Yeah?
Yeah, I guess on Monday.
Yeah. Okay. So hopefully we'll meet again sometime in the next couple of weeks. Okay?
Yeah, okay. Thank you so much.
And thanks for the participation today. Okay, I'll